want to talk about the implementation of the Community Centered Design Challenge that we're doing as part of WISE Engineering. Donna is an expert teacher in mathematics, and she has implemented this unit in her classroom several times, and it's her perspective that we want to gain from a teacher, knowing what to do and how to prompt and support the children as they go through this design challenge.
First, we look at the initial problem, the Community Centered Design Challenge, and they read it, I read it with them, and I ask them to sift through as we're reading it and to underline what they think are going to be important factors. I have to isolate what the main problem is, and as all good engineers do, we have to, in some way, discriminate between the specifications and the constraints in a design challenge. So the way that I do that with the students that have found very useful is I ask them first, go back into the original challenge, and why don't you let us know what it is that the design has or does. And we brainstorm, they speak to each other, and then they brainstorm, and I put that in one column on the whiteboard. And then I make a second column, and I said, now that you think you have all the things that it has or does, what are some things that you feel are limiting to you in this design challenge? And I then put all that in a different column, and I don't title the columns on purpose. And then I ask them, when you look at these two columns, do you see any differences? And so far, over the years that I've done this, the students have come to conclusions that one has more verb feeling to it, it's more doing, and one has more of a restricting feel to it, where they feel like they have not as much time, or they have to spend some money on materials or whatnot, or it has to be a certain dimension, and we then put names to those, and we say all engineers call the things that it has or does specifications, and the things that are limiting them in the design challenge as constraints. I show them on Smartboard usually some of the characteristics of FabLab Model Maker, and then I put them on the computers in teams, and they are asked to look at various pieces of mathematical shapes beforehand in the classroom. Say the pencil holders, what are those? The globe, what is that called? What do you notice about that? And we go through and we try to chunk like shapes together, like 3D shapes together, and ones that don't have anything in common apart, like how is a cylinder like a cone with its properties. And then I have them go on FabLab Model Maker, and they go wild with the 3D shapes. And I give them the sheet here, which says it kind of guides the experiment, the exploration, where they look at they have to look at actually three 3D shapes, and then since we've already in class talked about the properties of three-dimensional shapes, they then have to analyze it by turning the shapes around, etc., and come up with what they found on Model Maker, and it gets them into the program right away, which I think is a really good connection with the math and the simulation. And it's important also that the parents also see what it is that they're doing and how the mathematics is really tied to real life. So I like them to share what they're doing with the parents at home as well, and they have to list some geometric solids, and then they have to research on the internet and look at research some buildings that have the solids that they have listed in the buildings.
Well, that's neat. And then they come in and they paste them or
have to show
import them somehow.
Absolutely. In every respect, there always has to be an artifact of their learning. There has to be evidence of their learning. So they know that. So they then take their research, and then they have to say what shapes, what 3D shapes are within the buildings that they researched. and they see that how closely connected mathematics is to engineering. I find that it's very important that students have models to brainstorm ideas and get ideas from. So I give them a geometric solids sheet so that when they're home, they can say, oh, that's called a sphere. Oh, right. When it has two circular faces, it's called a cylinder. Otherwise, you don't know what you're assessing for.
Right, and they may forget the terminology and want to make that connection, and this supports them.
Sketching is, I feel, an integral part of the engineering design process. Students have to label, and before we even talk about sketching, again, modeling is so important. So I model for them, asking them, I don't just tell them what it is, but I say, what do you think goes into a good sketch? And I serve as the facilitator as we talk about what a good sketch is. If I was in New York and you were in California and you were trying to describe something to me, what would be the labels on it that I would be able to re-sketch it almost perfectly? So we talk about dimensions, we talk about numbers, we talk about how every piece of a building, the type of 3D shape it is, has to be labeled. And that is just driven home time and time again. But it also helps the students with spatial visualization. They start to really put ideas of three-dimensional shapes down on paper in a two-dimensional form. So I get to see in so many respects who has struggles in spatial visualization, who doesn't, and that's a great assessment for me as well. And we get to see the work of an engineer. You take a survey with students beforehand about what engineers do, and a lot of them say they fix cars. And at the end, you want them to say one of the verbs is that they sketch their ideas out.
They can also then go to Model Maker and do some sketching on Model Maker as well.
That's right. And then we want them to go to the control print screen and save that model that they've made and print it out and copy and paste it onto, again, right behind that sketch, so we can see that they are moving from the paper to the program, and they're able to take their idea from paper and actually transfer it into the simulation. And they absolutely love it. If you don't create cognitive dissonance, it's not a good engineering design challenge. And this I find to be such a great challenge, because we're saying, okay, life is not perfect. We're going to throw in some monkey wrenches here, and you thought that everything was so easy. Well, no, we're going to put some more specs and constraints in here, and the more the specs and constraints, the more problem solving abilities there are for the students. So we do up the ante, as you said before, and now we say that the skyscraper must have a certain volume between a range of 150 cubic centimeters and 250. And not only that, but guess what? You also have to be concerned about the surface area as well. And the surface area is between a certain range as well. So now what do? I have this chart of specifications and constraints that we did at the very beginning, and now I have to add to it. So what I like to do as a teaching tool for the students is have them go back into their text, go back into their original specification, spec and constraint chart that we did earlier, put everything originally in pencil, the original ideas, and then the new specs and constraints that came down will be done in either pen or a different colored pencil, so they can see the add-ons.
Right.
Visually. And this is where, when something is very heavy into a connection between mathematics and engineering and design, we have to always remember that the knowledge skill builders that we put in are going to take you out of the design challenge for a little while, so you can teach the math and then make sure that that math is connected, so then when they go back in to the design challenge, that they can actually make that connection and apply that mathematics in that situation. So here, obviously now surface area is a huge a piece of this design challenge. So we go through, what is area? What does area in this classroom look like? What things did a professional that did made something in this classroom, where who had to deal with area? So they talk about the floor tiles, we talk about the whiteboard, the tops of the desks, and then we look at shapes and we talk about squares and how area is measured in squares. We look at square centimeters, square decimeters, square everything, so that we don't create a misconception that it's just square 1 unit, like square inches. And from that point on, we use the model that's on the sheet, and it is a model of a parallelogram, and we look at what I like to do first is I have the students measure a rectangle with squares, and they get the answer, and then we try to develop the formula for area, which they do very readily, and then we took for area of a parallelogram or rectangle, and then we go into the different two-dimensional shapes, the different polygons, triangle, circle. What does a triangle and the parallelogram have in common? So what do you think? How does the area of a triangle relate to the area of a parallelogram? Why would it be half? Based on and another big piece of this for me was to watch out that I just didn't give them samples of right triangles, but we looked at other types of triangles as well, because then you have to have that height line drawn.
Right.
And
so if it's a scalene triangle,
how
or
are we gonna
isosceles
how are we
triangle,
gonna find out the area? Where is the height? And is base always on the bottom? So all those pieces we really deal with a lot, so that students don't walk away with misconceptions. And then of course we go into area of circles. But before we even do the area of circles, I have the students explore all different types of circular objects, like tops of plastic containers, tin can tops, soda cap tops, and we give them string. I give them string, and they look at relationships between the diameter of the string and how many times that goes around the circumference of any of the circles they're given. And they come up with a general consensus that, wow, it doesn't make a difference the size of the circle. The diameter of the string goes around 3 and a little bit more times each time. And isn't that interesting? And that happens to be a very important finding, and we talk about pi, and then we go into the area. So we really try to build understanding before they do the mathematics. But as you can see, when they do the formula and discover the formulas and they do the work, number one, it's very important that the teacher gives the dimensions. Otherwise it gets unwieldy. So if I'm going to make this 8 and this 4, everyone's going to have 8 and 4. And if this is going to be a diameter of 16, we talk about the radius being 8, etc., then everyone's going to do that, because that comes to be important later on down the road. And the other piece of this, which is extremely important, which a lot of times we don't talk about, is the properties of each shape. What makes a triangle so different than a circle, etc., etc. So they have to then bullet and write some properties for each.